We start with a review from the previous class. In the previous class, we defined the Apollonius circles of a pair of distinct points in C bar. Somehow, we just started with two distinct points, kind of without assuming they are fixed points of anything, right? I mean, kind of just 2 points, and then we defined what an Apollonius circle with respect to these 2 points is. Of course, later the idea later on is that when the 2 points are fixed points of some Möbius transformation, the Apollonius circles play some role, either as a curve stable under the action of all the integral powers of a Möbius transformation with these two fixed points, or as a family being permuted by such integral powers. So the definition, I mean, we started calling them, Apollonius circles, even before knowing they are actually circles, at least in general. And so for 2 distinct points and a positive real number, the corresponding Apollonius circle, let's say centered at both points with respect to this parameter R, is okay. In the two, there are 2 easy cases, which is when one of the 2 points is the point at infinity, in which case the corresponding Apollonius circle is simply a circle centered at the other point, the point which is not infinite, and then with radius just r or 1 over r, depending on whether it's the second point infinity or the first point is infinity. Right? But in any case, when either of the 2 points is infinity, the Apollonius circles centered at both points are simply the Euclidean circles which center the finite point. Those are obviously circles, but there is one case where we define them, and at least it's not so obvious that Apollonius circles are circles, namely when the 2 points are finite, in which case, and then forget for a moment about this topological closure, ignore it for a moment, because then the Apollonius circle is the geometric locus in C bar, with the property that the ratio of the Euclidean distances of the point in that locus to the two given points is constant, right, for this R. That's not so obvious, not as obvious as in the first 2 cases that such object is a circle, right? And notice that when in the special case where I have here equal to 1, right? Again, ignoring that topological closure, just taking into account the set. This geometric locus is the mediatrix of the 2 points, right? Because it's the set of points Z that have equal Euclidean distance to both points. If here I have a 1, that's the mediatrix, right? And what I do is with this topological closure is in that very special case, I just adjoin the point at infinity. So somehow this topological closure is really needed only in the specific case where I have a 1 here, and it's just so that I indeed have a circle in C bar, because I just put infinity in the set. Okay. Otherwise, if R is different from 1, I actually this set is already closed. Okay, and then the statement is that I mean, kind of the first thing I want to show is that these are indeed circles in C bar. So to do that, what I do is I take any 2 distinct points, and then I take any Möbius transformation that put kind of, okay, the inverse of a Möbius transformation that puts both in convenient locations. Right? The inverse of tau here puts z0 in 0, sends z0 to 0 and z1 to infinity. Right? So, but I consider the inverse, so this tau. And what the theorem says is that both, if I take an Apollonius circle of 0 infinity, the image is an Apollonius circle, but of my arbitrary pair of points. And this already tells me that these ones are circles, right? Because at least in the case where one of the points was infinity, it was obvious that Apollonius circles were circles. And conversely, right? I mean, if I take an Apollonius circle of my pair of points, then when I use tau inverse to sort of recenter things around 0 and infinity, I obtain an Apollonius circle of 0 and infinity. So these are indeed circles in C bar. The proof is I would say more or less standard. And then you see now that I know that for any two distinct points, every time I send them to 0 and infinity, Apollonius circles correspond bijectively by the Möbius transformation that does the job. Well, I can move from an Apollonius circle of a pair of distinct points to an Apollonius circle of 0 infinity, and then from there to an Apollonius circle of another pair of distinct points. So I obtained this corollary, which says that if I take any two distinct points and any Apollonius circle of them, and any Möbius transformation, right? So not even assuming that W0 and W1 have anything to do with the fixed points of nu. The image of the Apollonius circle of this one is an Apollonius circle of the images, these two images. So in other words, every time I have two distinct points, Möbius transformations always send Apollonius circles to Apollonius circles of the images of the 2 points. Right. Now next, if I have my two distinct points in C bar, I have the Apollonius circles, and then there is another family which is easier to define, which is the family of circles that pass through both points. That's easier to define. They are obviously circles. And you see by sending the 2 points to 0 and infinity, you see Apollonius circles correspondent to Apollonius circles, which are circles centered at 0. But then the common circles of my 2 points then correspond to circles in C bar that pass through 0 and infinity, that is simply straight lines through the origin. And these straight lines through the origin are obviously orthogonal to the circle centered at 0, to the Euclidean circle centered at 0. So when I apply my Möbius transformation, the inverse, right? When I go back to my 2 points, what I obtain is that the family of Apollonius circles, each of them is orthogonal to each of the common circles through the 2 points, just by conformality of Möbius transformations. All right, and so having these two families, having this pair of orthogonal families of curves, each of the families, by the way, foliates everything, C bar minus the 2 points. Once I have that notion, now I take my arbitrary non-parabolic transformation, different from the identity. And then if it's elliptic or hyperbolic, I define the Steiner grid of nu to be this pair of orthogonal this pair of orthogonal families of circles, right? The family of Apollonius circles and the family of common circles. And if the transformation is loxodromic, then I define the Steiner grid to be the pair of families consisting of, on the one hand, the Apollonius circles of the two fixed points, and on the other hand, the loxodromes that connect the two fixed points, that go from one fixed point to the other. And these are kind of just the loxodromes obtained by first mapping the two fixed points to 0 and infinity, then taking the loxodromes that we had already defined explicitly, and then mapping them back. Right? So, okay. And what happens is that in the first two cases, in the elliptic and hyperbolic, the Steiner grid, which is in both cases it just consists of the Apollonius circles around the fixed points and the common circles of the fixed points. Well, in one of them, in the elliptic case, the Apollonius circles are stable under the action of the integral powers of the transformation, and the transformation permutes the common circles. And in the hyperbolic case, it's the other way around. The Apollonius circles are permuted by the Möbius transform, by the integral powers of the Möbius transformation, and the common circles are, each of them is stable under the action. And we saw some like animations, right? So some examples. In the loxodromic case, each of these loxodromes, and it's not they are not arbitrary loxodromes, right? Because they are defined in terms of the multiplier, right? So they are not arbitrary. Right? In this case, these loxodromes that certainly depend on the multiplier, hence certainly depend on the given loxodromic Möbius transformation. Each of them is stable under the action, and the family of Apollonius circles is permuted. If you consider also the family of common circles, that's also permuted. So for somehow here I could have taken the other family, right? But somehow it seems to me that the Apollonius circles sometimes are more interesting. Later on, we tackled the problem of finding a numerical invariant that can be easy to compute and can tell me the type of a Möbius transformation with a simple computation. And we said that we wanted such invariant, but also in such a way that it could separate non-conjugate standard examples as much as possible. And then we did some some obvious considerations, and we realized that we know a function that is invariant under conjugation of matrices, namely the trace. And then with the other obvious considerations, we arrived at a formula, at a function, at a numerical invariant, a function that to each matrix associates certain complex number. And we saw that it is possible to determine the type of the Möbius transformation of the matrix. It is possible to decide the type of the Möbius transformation depending on where this number is located. We saw that a Möbius transformation is parabolic precisely when its Möbius trace is 4. Right? We noticed that all parabolic Möbius transformations must have the same. We noticed that all Möbius transformations are conjugate mod C bar. Hence, whatever function I was looking for has to have the same value in all parabolics. So somehow, in a way, it's kind of this is kind of expected, that it somehow collapses all parabolics onto one single value. But we saw that the Möbius transformation is elliptic precisely if the value is in this closed open interval, hyperbolic if it's in this open interval, and loxodromic if the value like lies completely outside. And then here's kind of the picture that one has to have in mind for those Möbius transformations with exactly two fixed points. Kind of the relation between where its multiplier is located and where the value of its Möbius trace is located. And the point, one of the points is that it really is, you see, it really is a very simple formula. It really is. If I give you any matrix, this computation can be performed immediately, like right away. Then some homework, and then to hand in, well, decide the type of the Möbius transformations of these matrices. So it's kind of many matrices, right? It's 10 of them, but somehow, well, I mean, you have something, a simple formula, right? So it shouldn't be that hard. And then I warned that this fourth exercise, think about it, because it's actually a hard problem. Okay, so that's the review.